So thanks again for the organizers for giving me the opportunity to speak and for organizing this workshop. Today I want to tell you a little bit about the results from a paper we just put out last month. The preprint is here. This was work done in collaboration with Danilo Ortigas and Jakub Milcharek. Let's see. Yeah. So in the big picture, we're considering generalization away from flat phase spaces to curved and nonlinear phase spaces. So a kind of a cartoon of that is pictured down here. So a flat phase space is usually described by 2 canonical coordinates or 2 times n canonical coordinates. So in this picture, we have this red square, which is parameterized by the canonical coordinates phi and pi phi. And we're asking the question, what happens if this flat phase space is really some approximation to a larger curved phase space, some nonlinear phase space? So in that way, this red square would be like the tangent space to some curved manifold. In this case, in this picture, we're choosing a sphere as the curved phase space. So maybe this is like the block sphere or something like that. So we're motivated to go in this direction by several reasons. So mainly in a lot of different areas of physics, compact phase spaces show up. So for instance, in loop quantum cosmology, one finds a compact phase space in the sense that the phase space is cylindrical. So the phase space is polymerized in the momentum direction. In nonlinear sigma models, one also finds curved phase spaces. So in nonlinear sigma models, the field value takes values in some curved manifold. We're also motivated by the fact that semiclassical descriptions of finite dimensional Hilbert spaces correspond to compact phase spaces. So this is kind of an interesting point because, you know, many systems might have an infinite dimensional Hilbert space, but this might be an approximation to some finite large dimensional Hilbert space system. So this is kind of a big motivating factor. We're also motivated by the fact that in a system with a compact phase space, all physical quantities are bounded. So, you know, if the phase space is compact, there's no way anything can diverge. It has no room to diverge into. So that's a big motivating factor. And in fact, this shows up in loop quantum cosmology because the momentum direction is compactified. The Hubble parameter can't diverge, and one gets a big bounce instead of a big bang. We're also motivated by the fact that for a system with a compact phase space, the dimension of its quantization, the Hilbert space, is less than infinity. So this makes defining things like an inner product a lot easier. We're also motivated by this Born reciprocity symmetry. So this is just a kinematical symmetry between position and momentum. So, you know, in an ordinary system, one can swap position and momentum at the kinematical level by a canonical transformation without changing the kinematics. And this is a symmetry that's kind of broken at the dynamical level in a lot of systems. But by implementing this curved phase space, we can restore this in certain situations. So that's kind of a motivating factor. In the recent years, there's been kind of a lot of development in this area. So in particular for cosmological models, compactified mini superspace models were explored here by Artigas, Rovelli, and Milcharek. One of the main findings there is that when one compactifies the phase space of gravity in a cosmological setting, one finds not only a big bounce, but also a big contraction. So in this setting, the universe has a maximum volume it can reach before it starts contracting.
I have a question. Why the perturbation theory was done earlier than this mini superspace model? It should be the other way around.
Oh, yeah. Yeah, so to tell the truth, I'm not sure about the history. But I think probably initially there was more of an eye towards condensed matter experiments, and that's closer to field theory. So that's probably why cosmological perturbation theory was explored first. But I think Jakub was there.
I have a comment on that.
Yeah.
I mean, concerning the mini superspace, that was in actually the gravitational degree of freedom, which was compactified. But in case of perturbation, that was analysis of the test field, scalar test field, not the gravitational degree of freedom. Okay, so that was actually a simpler thing.
Yeah. Okay. So Also, connections with condensed matter models were explored. So, for instance, in this paper here, there's a correspondence between condensed matter models and scalar fields. So many different varieties of Heisenberg models turn out to limit towards scalar fields in the limit where the phase space curvature goes to 0. And in particular, for the Heisenberg XXZ model, it's been shown that this model directly limits to the Klein-Gordon field. So this model has relativistic symmetries in it. It's just that you need to take the phase space curvature to 0 in order to see them. And currently, we're working on the relativistic spin field theory. So we're asking the question of how we can put an Ising model, say, on a curved background such that this spin field actually has covariant symmetries built into it. So that work is to appear hopefully pretty soon. And the eventual goal of this program is to, of course, compactify all fields used in theoretical physics. So that's the direction we're exploring. So let's talk about how one can do ordinary mini superspace cosmology with this sort of thing. So maybe we can start with just this simple constraint, this Hamiltonian constraint here, just described by the volume and the Hubble parameter. So this is just ordinary de Sitter cosmology. So we have a cosmological constant here. And the volume and the Hubble parameter are affine phase space variables, and they have a almost canonical Poisson bracket up to this factor of -1. And we're asking what the compact phase space generalization of this is. So in order to kind of motivate that, maybe we can just show the compact phase space generalization of a harmonic oscillator, for instance. So if we start with this precession Hamiltonian here, which describes the precession of, say, a particle with a spin, if we take the limit that the spin goes to infinity, we get back this harmonic oscillator Hamiltonian. So this is kind of a motivating factor for us. We can sort of choose things in such a way that the compactified Hamiltonian is as simple as possible, maybe takes a polynomial form. So we're compactifying this Hamiltonian here. One possible compactification is the following, where we're introducing two scales, LV and LH, and these are parametrizing how big the volume and the Hubble parameter are. So we're essentially choosing a spherical compactification of the phase space, and we're parametrizing this spherical phase space with spin variables. And the parametrization is given here. So this is just essentially, cylindrical coordinates for a spherical phase space. It's a little bit weird that we're using cylindrical coordinates for the phase space because it's spherical, but it turns out that we do this because we want to enforce a canonical bracket between V and H, and it's really only possible to do that if we have a cylindrical phase space. But anyway, if we start with that Poisson bracket I showed earlier for V and H, and we just directly compute the Poisson bracket between these functions, we find that they obey the normal SU2 bracket, provided that LV and LH multiply together to make S. And doing that, we get this compactified Hamiltonian here for the cosmological degree of freedom. And this has a polynomial form, which is good because it's simpler to quantize, for instance, and it could also be implemented in condensed matter systems because this is a simple form for the Hamiltonian. And furthermore, it has the correct limiting behavior as the phase space curvature goes to 0. One can do quantum mechanics on this just in a kind of straightforward way, just by doing the canonical quantization. The only hang up is there's an ordering ambiguity, just because you have this product between SZ and SY squared. But to get around that, we just choose the Weil ordering, so we essentially just average over all possible orderings. And from there, the dynamics are determined in a simple way. We just look for states that are annihilated by this operator. And just as an example, we can consider the matrix form of this operator in the simple case where the parameter S is equal to 2 H bar. And just to find this other parameter, delta is lambda over LH squared. We get this form for the Hamiltonian operator. And of course, this operator can be diagonalized and solved in the case where the dimension is small. But even despite the symmetries this matrix possesses, it's not possible to diagonalize in the case where S is very large compared with H bar. So in that case, we need to do something else. So like I said, it's possible to do analytic stuff with this model when S is comparable with H bar, but ultimately we want to explore the regime where S is much, much larger than H bar, because it appears that the universe is well approximated by a flat phase space. So it should be that the phase space curvature should be low, meaning S should be large. So we want to focus on systems that have a large S. On the other hand, it's hard to deal with these systems at the analytical level. So we need to implement some sort of perturbation theory to extract effects. And so we're going to do semiclassical perturbation theory because in this context, we're really interested in quantum effects. So our method of choice for this is, of course, the canonical effective methods. This is a canonical matter system for spins, so it makes sense to use this. And so essentially what we're doing is formulating the dynamics not in terms of state vectors, but in terms of expectation values of phase space variables and their moments. So when I say moments, I just mean, wild-ordered expectation values of fluctuations. The Hamiltonian generating the dynamics for these things is given here. It's just the expectation value of the Hamiltonian constraint. And if you do some algebra on this, you find it's just the classical Hamiltonian plus some quantum corrections, which are parametrized by the moments. The Poisson bracket determining the kinematics is just this one. It's not a Poisson bracket yet. We need to augment it with the Leibniz rule, but that's kind of not an issue. So that defines the kinematics, and the dynamics are determined by this Hamiltonian. We are making a certain assumption on the state. We're assuming that moments of this form are a certain order in H bar. So in this way, we can make a semiclassical truncation. So that's where the approximation comes in. But with all these ingredients, we can write down the equations of motion. It's just normal Hamilton's equations here. So maybe we can talk a little bit about this Poisson algebra. It's mostly linear algebra, except for the bracket between the two different moments, which is nonlinear. So this is kind of a non-trivial algebra. It's not a Lie algebra. It's really just a full Poisson algebra. The dimension of the algebra is 9, but the rank is only 6. So actually, there are 3 independent Casimirs that are conserved for all Hamiltonians. For the most part, we can guess the first one. It's just the expectation value of the spin squared, which isn't surprising because this Poisson commutes with all Hamiltonians formed by spins. The other two were found kind of by brute force methods, just using Mathematica scripts and hand calculations. The most interesting one is C3, which is the determinant of the covariance matrix. So this is kind of like the volume of the wave packet in spin space, if you like. So we can kind of use this as a measure of semiclassicality, and it's conserved for all time. So that's kind of a useful thing to know. So we're doing this semiclassical analysis. Maybe we want to do a deparametrization first. So we have the kinematics. Let's talk about the dynamics. The classical constraint is the same thing I showed you before. Deparametrization is kind of non-trivial because there's no standard matter sources. We don't have a scalar field really. So what we do is we kind of play a trick. We introduce a scalar field such that its momentum is this constant lambda LV squared, such that this P phi is canonically conjugate to the scalar field. And then we can use this scalar field phi as an internal time and use that to deparametrize. And when you do that, the deparametrized Hamiltonian is given here. It's just sy squared. So that's kind of an easier thing to deal with. And I guess we can proceed in 2 different ways. We can quantize before or after deparametrizing. And it turns out in this scenario that the 2 approaches agree. So quantizing before deparametrization is kind of a little bit harder, so maybe we should talk about it. So the expectation value of the Hamiltonian constraint operator is given here, and we should of course constrain that it's equal 0. But it's not enough to enforce this constraint is equal 0. We also have to consider other constraints, right? Because this Hamiltonian constraint operator annihilates any physical state. So this thing should also, of course, equal 0, but that being 0 is implied by the expectation value being 0. So we get actually a whole family of constraints that we need to satisfy. Nevertheless, we can solve the constraints to leading order, and this is the deparametrized semiclassical Hamiltonian that we find. It just depends on the dispersion of sy squared. And like I said, this agrees with the quantization of the deparametrized Hamiltonian. So with that set up, the equations of motion are kind of easy to write down. They're just the usual Hamilton's equation. And these equations end up being nonlinear because the Poisson bracket is nonlinear. But nevertheless, we can still solve the whole system of equations because there are so many constants of motion, right? We have Sy and its dispersion being constant. This just comes from the dynamics. And of course, the Casimirs are conserved. So we can solve this whole system exactly. And just as an example, this is what we find for the volume as a function of the internal time. So the first term is the classical term, which is just a trig function. Yeah, that's there. Phi should only take values in the range where cosine is positive because this is a volume. So that's something to keep in mind. The semiclassical correction is shown down here. This correction is parametrized by the relative fluctuations of Sy squared. One thing we notice immediately is that these perturbative corrections depend linearly on phi. So actually, these semiclassical corrections are growing with time. So ordinarily, this would signal the breakdown of perturbation theory, but because we're only considering phi in a finite range, this kind of isn't a problem for us. But if we make this model more detailed, this feature might kind of cause some complications for us down the road. Okay, so let's talk about just kind of an immediate application of these results. So it turns out we can actually say something about the Bousso bound by considering these semiclassical corrections. So we have this parameter epsilon, and we can essentially calculate this in two different ways in order to say something about the Bousso bound. So we can calculate epsilon just as the relative fluctuations of Sy squared. And according to that canonical mapping that I showed you earlier, this is related to the relative fluctuation of the Hubble parameter, which is in turn related to the relative fluctuation of the Hubble radius. On the other hand, we can estimate the value of this relative fluctuation of the Hubble radius. If we just imagine that fluctuations of the Hubble radius are of the size of the Planck length, and of course the Hubble radius in a de Sitter universe in the flat range is related to the cosmological constant. On the other hand, this is of course related to the area of the Hubble sphere, which should be bounded from below by 1 over the number of degrees of freedom on the Hubble area. And that last inequality comes from the Bousso bound, right? That's from that conjecture. So in that way, an independent estimation of epsilon can give us more insight into this Bousso bound. So maybe we can just estimate that in a rough sort of way before wrapping up. Say we consider the state of the universe as a condensate of qubits. So we're considering the universe as being described by qubits right now. Whatever kind of bit we choose to describe the universe isn't so important. It just has to have a finite set of states that it can take on. So that's what we're dealing with right now. Let's say we're in a condensate state where all the qubits are pointing upwards. So that's kind of a reasonable assumption just for a rough calculation. And furthermore, we assume this compactification scale for the Hubble parameters like the inverse Planck length. So this is something we get from loop quantum cosmology, for instance. That's kind of an assumption we're working with. And with these ingredients, we can just directly calculate what epsilon is from kind of first principles. And this is the thing we find, right? So 1 over lambda times the compactification parameter S. And we can compare this with our result from earlier, and we find that the number of bulk degrees of freedom, which is just S divided by S, H bar, sorry, it's related to the number of qubits, is this thing here, which is much, much greater than the Hubble area divided by Planck length squared. So it appears we would be violating the Bousso bound in this case. And so we have to resolve this discrepancy.
Sean, there is a question from Sudo.
Go ahead, Shudo.
So the S here is the entropy in your
equation? S here is the compactification scale.
The compactification scale, right? Okay.
Yeah.
So that's independent. So that's just the length Planck inverse is like, it's independent of the number of degrees of freedom. Like it doesn't depend on if the degrees of freedom increase, it doesn't change accordingly or anything like this, right?
Actually, so in this case it would, right? Because we're considering the state as a condensate of qubits. So in that case, S is really just N times H bar.
Okay. Okay.
Yeah.
Okay. I understand. Thank you.
Cool. Thank you. Yeah, so maybe just wrapping up. So just saying what we did, we used these canonical effective methods to analyze quantum fluctuations of the compact phase cosmology. And we found that these semiclassical perturbations were kind of unstable over long time scales, much longer than the time scale of the universe. So this kind of wasn't a problem for us because we were only considering fluctuations in a finite time range. But if we include ordinary matter as opposed to just this dark matter, we might see bounces and contractions, which would allow these fluctuations to build up over time. So that's something we have to look out for in the future. And furthermore, we were kind of at a loss here because it showed that this Bousso bound wasn't satisfied for our considerations. So we kind of have to resolve that, and a couple ways we can do that are the following. We might consider the state of the universe might be not semiclassical in the sense that the moments of the spins aren't proportional to h bar. So that's one thing we can do, but then we kind of have to abandon this notion of semiclassicality. It could be also that the compactification scale isn't Planckian. So in this last slide here, we were assuming the compactification scale for the Hubble parameter was Planckian. If we get around that assumption, we can also consider not violating this Bousso bound. And this last point I'm just mentioning because there have been a few papers over the last month by John Barrow considering that the Hubble horizon might have a fractal-like structure. And I'm only mentioning this because the upper bound he finds for the number of degrees of freedom in the universe is precisely the one we find from our semiclassical consideration. So that might be one other way we could resolve this tension. But anyway, I'll wrap up here and say thanks, and I'm happy to take any questions. Thank you.
Thank you, Sean. So are there any questions, comments? Another question by Sudo, right?
Yeah, so there might be also this resolution that you mentioned for the Bousso bound. One thing might be that you don't get an accelerating solution. Is that possible? Like you don't have a quasi-de Sitter phase? I mean, you already assume that you have one, right?
Yeah, so we assume we have a quasi-de Sitter phase.
Right.
It could be that if the compactification scale is made small enough, this phase lasts for less time, but this is something that needs to be checked. Yeah.
Yeah, what I mean is that there might be some sort of tachyonic instabilities, and this is not a de Sitter minimum, but maybe some sort of maxima. And then if there are tachyonic instabilities, then there's not a good meaning. I mean, there's no good way to express what you mean by a horizon if it's not semiclassical. So you kind of hint at that in your first point. But I mean, what I want to say is like, there might not be semiclassical description of a de Sitter space in that sense, in that precise sense.
Right. I understand. So that's something that also needs to be checked, right? Yeah. Good point. I agree.
There is a question by Martin.
In the same context, do you really need all the delta Si as J to be about h bar, or is it just this delta Sy squared?
Yeah. So this is the moments being proportional to h bar here are kind of an assumption based on this condensate state. So for instance, here, if we chose delta as z squared, we would get 0, right? Because then the dispersion is equal to 0. So we don't need for sure all the moments are being comparable to h bar, but having some of the moments comparable to 1 would be a kind of a bad thing.
Okay, but it could be something like a spin version of the squeeze state in which delta Sy squared is suppressed compared with other second order moments.
Yeah, it could be something like that. I agree.
But decoherence might often lead to squeeze states, so that might actually help you if it goes in the right direction.
Good. Thank you for the point.
Just a comment that this is a rough estimate. What's assumed here is that what we are counting basically here is the number of spin 1/2 particles contributing to the spin s. Okay, so qubits in other words. But nothing more is said about the details of the state.
Yeah, it's a pretty rough calculation. So we're just assuming some generic state and seeing what we get.
So any other questions? So if not, let's thank Sean again.